shall I start?
Yes, ma'am.
Shall I start? Good afternoon, everybody. We are starting post-lunch session, and the resource person for today's post-lunch session is Dr. Arjun. Sir is with us. So I request Dr. Hemchandra to give a brief introduction about Dr. Arjun. Sir, please be seated for 1 minute.
Good afternoon, everyone. Today we are in day 4 afternoon session from 2 p.m. to 4:30 p.m. So today we have resource person Dr. Arjun. He has done his MTech from MIT Manipal and PhD from NIT Karnataka Surathkal, and he has postdoctoral researcher from in 1 year in IIC Bangalore, and he has technical director for Apsaram Technologies Private Limited in Karnataka. Later now currently is working as a specialist in Bosch Technologies Bangalore. So in this I welcome Dr. Arjun sir with a flower bouquet.
Chandra was my senior actually. So I feel embarrassed when he calls me sir. And thank you sir for the very short introduction, because otherwise introduction is the most embarrassing for any person who's on dais. Okay, thank you so much, and thanks MSRIT for the wonderful hospitality. It was really nice to be here. Okay, coming to today's topic. Before I deal with the topic, so you're all faculties and PG students and research scholars, right? That's how I understand. Right. So I've done a little homework before coming to MSRIT, talking to people, talking to Chandra sir, and talking to other resource persons about the participants, so that it helps me deliver the topic more effectively and better. So today's topic is design of controllers. If you've looked into the brochure, I gave the topic as design of controllers for electric vehicles using frequency response techniques. That was the topic. That's what we're going to do. But I just put the PPT as design of controllers because whatever I'm going to discuss is not just applicable for electric vehicles, it's much more than that. Okay? So what I would want you to take away today when you walk out of the doors is that you have a very generalized approach to power electronic problems. You don't have to look at it this way, like look, this power electronic converter is being used for electric vehicles. This power electronic converter is perhaps being used in let's say for general automotive sectors, or let's say for aerospace applications, or let's say I'm developing a power supply. So it's not that way, right? Your approach to power electronic or to solve a problem should be look wherever it is, wherever the converter working from the control perspective, it's just going to remain the same. So what is important is two things: understanding the problem statement, right? Looking at the constraints and getting it to mathematical domain, and analyzing in the mathematical domain and making a map to the physical domain, right? So this is very much applicable when I'm talking about controllers. So wherever is the application to, let's say I'm designing a power supply for some propeller applications, aerospace, or let's say I'm designing a power supply for an electric vehicle. From the point of designing the controller, it's still going to remain the same. Now what is going to be different is the constraint that we are operating with. Okay? So I'll just give you an example. Now this example is to help you understand that from the control perspective, wherever is the application, your approach to solving the problem should be same. That should be the attitude. It is not that, look, I am a power electronics engineer for specialized in only electric vehicles. No, that's not the way. Your capabilities or your specialization should be such that, look, whatever is the application, I have the knowledge to design the controller. You get it, right? Now what is the difference? What is the difference when it comes to application is only this much. Let's say you are working for an application, let's say it could be an electric vehicle or an aerospace application. What you should be looking at is, let's say this is the voltage, this is the time. What should you be asking your customer is, look, I just want this graph. What is this graph? This graph is voltage versus time. What is it going to tell you is, it's going to tell you too many things. It's going to tell you what is the steady state value, right? So it's going to supply you what is the steady state. Let's say 13.3 volts is my steady state value. Then what should be the settling time? Let's say he's very competitive. He wants the settling time to be less than 1.5 milliseconds. Okay? Let's say I'm talking about a 2 kilowatt converter, settling down in 1.5 milliseconds. Then what should be the overshoot? And there are some customers, they are very particular about this also. T1. If at all you have an overshoot, they want the overshoot to be within certain amplitude. Together, they also want this overshoot to die within certain time. Next, more stringent, how many such overshoots? and what should be the amplitude. They also give the ratio of the first amplitude to the second undershoot. Could be possible, right? So all you need is only this, right? It could go to an aerospace application, it could go to an automotive application, or you are developing a general APLA power supply, whatever it is. All you need is this. But once you have this, you should not really bother about where it is. Also, they could give you something about load dynamics. Let's say there is a change in the load changes here, right? When there is a load change, of course, there is a disturbance. So within what time should the disturbance actually die? What should be the amplitude of the overshoots and the undershoots, and what should be these times? That's it. So your job is to design, or you should have the competencies of designing controller with just this as the input, or maybe some other critical inputs, but not going too much in detail. But just with this, if you can design a controller, irrespective of the application, then you are a very good control expert, or a subject matter expert in control systems applied to power converters. Is that clear? So today's topic is, when we just walk out of today's class, that irrespective of any load that is being applied, but of course it's very important that you know the load dynamics. When I say this is the load dynamics, and you should know what the customer's requirement is. Is that clear? This is basically the voltage of a output voltage of a converter. So you have an input source, and then you have a power converter, and then you have a load. What I am talking is, the objective is to regulate this voltage, and this voltage is what I am talking about, right? Irrespective of, he is going to tell you about the source dynamics, that's important, which I am going to tell you in the later slides. Of course, the source dynamic is also important, but with respect to the load, if you know this much, and then maybe if you little understanding about the source dynamics, you should be able to, and when a converter is given to you, you should be able to design the controllers, right? So the objective of today's topic is just this. Are we setting the objective right? Is that clear? No problem, right? It's okay. It's there. This is what. Fine. How many of you are from power electronics background already? You are from power electronics. So you have done your masters in power electronics, and then what's your background now?
Masters in power electronics.
Power masters, and then your faculty somewhere?
Research scholar.
Your research scholar. Very nice. Otherwise, most of you are from power systems, controls, all of that? Okay. Power systems, mostly. Okay. So how, if I ask you to just say rate out of 5 on control topics, control systems that you've studied in your UG and PG courses, what is the rating that you can give out of 5? 3, 2.5, 4, whatever. Just generally. This will not help me to give you marks or something, but then just to understand what should I teach. Yeah. 2.5 to 3.5, somewhere between. So let's go then a little slow. Okay, the point is to understand. Now let's look at this power converter. Of course, whatever I want to do is not something really great or big. One thing you should keep in mind, or one principle that I am following, is no matter how big the converter is, no matter where it is used, they are all derived out of 2 converters, especially one. It's basically buck. Okay, please note this. It's a very bold statement and a very powerful statement to tell you that any converter, okay, is constructed out of a buck converter. So if you can really conquer buck converter, you have conquered boost. I'll tell you the reason why. Look at this converter, okay. Let's say this is a very stiff source. No? I will add a capacitor here. Will it make any difference?
No.
No, right? No. Simulation wise you cannot do. Simulation you cannot add a parallel capacitor to this, because simulation models assume that voltage sources or capacitors are stiff voltage sources. So you can't add two parallel sources. Like 3 volt and 2 volt cannot be added. You cannot parallel it. Forget it. But you add a capacitor. Let's say there's a small impedance, makes no difference here. So there is a capacitor here. Okay. Now let's say I'll go reverse. I'll remove the source here and connect the source here. And I'll remove this load here, connect the load here. Okay? Shall we draw this? You have a pen and paper with you? Let's start drawing. So I will look at this. Okay? I have added a capacitor, or let's say this setup. Okay? Capacitor in parallel with the load is put up here. This is put up here. Okay. So I have a load to the right, and then I have a capacitor, this combination, and then I have a source, I have a switch. You know this diode also works like a switch, right? Diode is working like a switch, right? This is also a switch. What is left is an inductor, and what you have is a source. Is that correct? What I've drawn? I have not changed anything here. Inductor is in its own position. Diode is a switch. There is a switch. So inductor is this. This is the point. This is called as the pole. I call this as a pole. And to the pole, there is one switch which is supposed to be a diode. And then there is one switch here. Got it? And this position, this point, I have just connected this load and capacitor. And then this I have got here. Is this clear? Any doubts here? Okay, now you look from left. Can you see what converter this is?
Boost.
It's a boost converter. Is that correct? It's as simple as that. So I have derived the next fundamental converter out of this. This boost. Now with this, you can also derive buck boost. Okay? So with you have buck, you have boost. If you intelligently club, you will get buck boost. You can try this as a homework, you can try take it. Okay? So you have buck boost and buck boost. Okay. Now, next fundamental converter is an inverter. Is that correct? You have all studied about voltage source converters, right? If you connect, you can take that also as homework. If you connect this converter to buck converters in parallel and operate them as if, you know, when one is on, the other is off. You got it? So let's say I have one more copy of a buck converter here, the same buck converter, and let them feed the same load. You parallel it. You got it? Two converters are being parallel. And now, how do we operate converter 1 and 2 is, when converter 1 operates, the converter 2 doesn't operate. You got it? Is that clear? If you do that, you will get an inverter. So, a simple H-bridge inverter, single phase, can be realized out of a buck converter. So, any converter is simply a buck converter. To give you more insight, I'll just draw this here. This is a DC source. Of course, you have diodes, right? These diodes are for negative currents. And then you have the load. Is that correct? Okay. Now, from the source, this is the same source. Okay. What is the connection from the source? From the source, it's going to a switch, correct? Correct? From the source, you have connection to the switch. Am I right? From the source, you have connection to the switch. Right? Now, the source, we call this as drain and source. Okay. From the source, it's connected to a diode, right? Can you see that? From the source, it is connected to a diode. Correct? Now, there is a junction here. The same junction is here. That's connected to what? L, C and R. Is that right? Do we have an LCR here? No, we don't have an LCR. Right? But what? This LCR, if I just move like this, okay, and just keep it like this, it is the same LCR, right? Right? Now this is LCR, right? Now let's look at what happens here. When I close the switch, right? If I close this switch or this switch, it's the same. Don't worry about what is on this side. Okay? I just close this switch. Let me call this switch as T1. Let it be the same switch T1. So the moment I close the switch, right? What is going to be the voltage here? You're going to get a positive voltage. Right? Of course, I'm closing the other switch also. I'm just telling you from the concept. The moment I open the switch, right? What you see here is also the same thing. Right? The moment you close the switch, this becomes open, and the voltage that you see at this is same as the input voltage. At least this fundamentals you have, right? Clear, right? Okay. So the moment I open the switch, right? This gets forward biased because the inductor has to find a path to the current. Otherwise, this inductor gets blasted. Same thing is here. When you open the switch, this diode gets forward biased because the current has to flow, and that is only possible with this diode. This diode and this diode is basically the same thing, right? Arranged in a different fashion. So what you see is basically zero. So the voltage that you see here or the voltage that you see here is basically the same. Is that clear? Very clear? Okay. Then this, what you want basically, you want a clear DC, right? You want a very neat DC here. Now you have a square waveform here and here at the same terminals. What I am calling this terminal XY, whatever it is. So you have a square waveform. And what is expected out of this is a clean DC. What do? You have to filter it out. Because Fourier has given you a wonderful analysis that, right, any waveform, if it is periodic, it is composed of a DC quantity and some sine quantities and some cosine quantities. Cosine quantities are sine. So I don't differentiate between cosine and sine. So what he says is, look, if you have any waveform which is first periodic, look, it has a DC quantity and it has some sine quantities. That means you can decompose it into some DC value and some AC value. So what I am interested in is only this. I don't want the AC quantity. I want only DC. Why? Because it's a DC-DC converter. Right? I don't want any AC quantity out of it. If it is an inverter, it's a different case. I want a DC quantity. So what do? You filter it out. And how should you filter? You give it to a low pass filter, and the best low pass filter, let's say second order filter. Correct? And you make sure that all of these quantities fall in this region. And what is DC? So you set your cutoff frequency almost very, very low, much lower than what you want. So it will only pass the DC. Is that clear? And what is the, let's say this is on for DTS amount of time, this is on for DS amount of time. Can someone tell me what is its average value? This is VG. You have a waveform whose amplitude is VG, and then on for DTS and on for 1 minus DTS. Can you average this waveform? If you are getting confused, you can take it as X and Y. These values are X and Y, whatever. Can you tell me what is the average in terms of X and Y? Average of a waveform? No, it's not 0. 0 is when you have positive and negative.
dg by 2.
It is just the area under the curve to the total area. Total area is TS because I am looking at the entire curve. And what is the area under the square curve?
Yes, beta.
What is the area under this? I have a square waveform, I want to find the area. A into B, so which is VG into D. VG into DTS. And that cancels, right? What you get is what? D into VG. Am I right? Making sense? So what did you do? You have a power converter, right? And what you were getting at this point was a square waveform, right? And what you said, look, it's a DC-DC converter and I want a DC out of it. And then we found out that the DC value is D into VG. So this A naught is D into VG. And I can do it physically. This is mathematically. Physically I can do by using the filter, which is a second LC filter, second order filter. Why a second order filter? The best thing is It has a very good attenuation. I'll discuss this in detail. So basically we are using an LC filter. You can ask why can we not use RC filter? An RC filter also does the job, but you look what this RC, this resistor is a bad component. You don't want it. Why? Because it creates loss. I don't want. From control perspective also it is a problem. I'll tell you what it is. But an LC filter is really good because it does not have any losses. This is the load. Anyway, that's where your power gets dissipated. So this is your DVG value. And you want to pass only this. So what you do, you set a cutoff frequency such that you only pass this. As simple as that. So the design is all separate. So that's the reason why at this point you connect an L, C and R. This is not just connected like that. It is just connected because you want to filter out the components. Filter out what you don't want. Now similarly, even here the voltage is the same. So when the voltage is the same, the business is going to remain the same. I am supposed to connect the same LC filter. So L and resistance and the load. So effectively, right? If I just model this as, if I remove everything, what converter is this? What is this converter? You had that converter in your previous discussions, right? VSC, voltage source converter. This is the same voltage source converter but single phase. If you add one more, you have one more phase. This is a single phase voltage source converter. This is used for DC to AC conversion. Correct? So what did we do now is, we have a buck converter. We saw the same buck converter looked into reverse is a boost converter. But the same converter, if you look at it here, becomes an inverter. Right? I can also do AC to DC like this. This is a DC to AC. Right? I maintain a good potential here. Than this, it's going to charge. What is this? Becomes, if I don't use any of these switches, right? If I remove these switches, right? I just remove the switches and then only connect the diodes. Becomes a rectifier. So we started with a buck converter, realized a boost out of it, and then we know, I gave you homework on how to make it buck boost. It's pretty simple. And then we also realized the DC to AC, and then we saw how DC to AC converter can be used as a buck converter. This is what we do in lab, right? That if you have have you seen? I mean, if your faculties, we have the semicron stacks. Semicron converter stacks available only for experimentation purpose for students. So where it's put in a glass box and they don't give you a buck or a boost converter like this. What they give you as an H bridge, they give you only this. They give you many switches like this, parallel switches, like this. And you can create a buck, you can create a boost, you can create a rectifier, you can create an inverter, you can create anything if you have the fundamental knowledge on buck converter. Is that clear? I can also realize a DAB using this. That's a dual active bridge. I can realize anything that you want me to, I can just use this and create. Is that clear? So that is the reason why today's class, we have taken an example of a buck converter. The reason being, if you can conquer a buck converter, you can conquer anything in power electronics. But believe me, 90 to 95% of the converters that you look in power processing units like CPUs, or motherboards, all are buck converters. Because you have a very high voltage with you, you should convert it to very low value, 3.3 volts, 5 volts. Right? Everything is out of buck converter. So if you want to really have your what you call career in the field of power electronics, and if you really want offers to just get lined up at your premises, just if you can somehow convince people you know buck converter well, any power electronics engineer who is sensible enough should admire you. Nobody wants you to talk of DAB or something very big at the big instance. What they want is, can you look at this big converter or complex converter and simplify it so that you can look at it as a buck converter? Because once you realize it as a buck converter, then your life is very simple. Every textbook discusses buck converter. But what is the point is, we talk of all very big stuffs, we fail to simplify it and connect it with what we know. Because the concept is at some very elevated level. You're here. How do you bridge the gap? Right? That is what is required and that is what is missing. When I interview candidates, we never ask rocket science or plasma physics or anything. No. What we ask is whether you know this well, whether you know how a switch works, have you taken things for granted in the beginning? All of this. How good you are with your circuits concepts. How good are you with controls? So today, whatever you discuss, I am not going to talk anything what you don't know, but you will soon realize we are constructing things out of what you already know. Irrespective of whether you are from power electronics or power system background, if I am able to convince you a topic today, then I am a good engineer. So the same thing is applicable to you also. Is that clear? So you know what we have learned all of this time is a simple buck converter is the most amazing converter that's ever built, because it is that converter which gets manifested into any converter that you want. Only thing is you should have a right mindset to look at it the way it is. Is that clear? Okay. So I could have taken an example of a LLC converter and discussed its characteristics, but that's not the objective. Okay. So let's go back to buck converter and look at its what we want out of a buck converter. This is going to be the hero of the today's session. This is what we want to achieve out of the buck converter that we have. Okay. So now what did we see is the output voltage of a buck converter is duty cycle times the input voltage, right? This is going to be the average output that you get. Now, look at this equation. Now this equation is a very important equation because my control design starts from here. It's a very basic equation. We all know, we have written 100 times, you have taught it to students or your pals. Now what if I want to control the voltage? It starts from here. This is how we think. Okay. Look, I want to control this voltage, right? This is what I want. If I want to control this voltage, what should I control? I should either control duty cycle or control input. Is that clear? Now, think, do you really have control over this input voltage? There are only two options, right? You can either control duty cycle or control input voltage. But I want to control my output. Now, which of the two components should I control so that I control the output voltage? That's a natural question, right? If I ask you, if I give you an equation and say, look, I want 13.3 volts, okay, and 13.3 should be equal to D into Vg. Okay, you will ask me which voltage do you want me to vary? Which quantity is constant? You want to ask this, right? Okay. Now tell me, out of the intuition, very common sense, you have a converter which is being fed from somewhere, some input, and then there is a duty cycle. The duty cycle is going to control this. Now, which of them do you think should be the control parameter and which do you think is not a control parameter? B is a control parameter, very good. And Vg should not be a control parameter because you are getting it from somewhere. Got it? I'll show you some real, I've got some real experimentation results to show you what happens with Vg, how notorious the Vg is. Okay? So Vg should never be a control parameter. So you should be ready for whatever happens in Vg, you should control V0. So much so that your control law should be like this. D should be equal to, let's say, V0 by Vg. The moment Vg varies, D should vary such that V0 remains always constant. Mathematically talking, if I call it as K, constant, right, D is equal to K by Vg, which is a variable. If you can control if you have very good control over this equation, then that means you are a very good control expert. So I should be controlling D so precisely that any variations in Vg, I should maintain this voltage constant as K. This is not easy. I'll show you an example as to what happens in real time. Is that clear? I should meet these requirements, but based on this. So you will see I will derive equations which can capture all of these dynamics. Okay? Okay. So So my output voltage depends on VG, correct? Input depends on duty cycle. Now there is this additional guy that is a load. See, always in electrical engineering, you don't define load in terms of resistance, correct? You define in terms of the current flowing through the resistance. Okay? So this is the load. So which means in bracket you can write R. Now this load also creates disturbance, right? But you can ask me a question. V0 is equal to D into Vg. According to this, it's not a function of load, right? It's not a function of load. Right? It's independent of the load. Is that clear? Where are we missing then? This guy says it's a function of load, and you also know very basics that this is our power converter, this is a load. Okay? Now let's say this is V0. If I short this, I'm going to short it. What will be the voltage across this? 0. But according to this equation, it's independent. Is that correct? Because here there is no function of R here. Right? Let's say into R, no, it's not there. But then you also know by intuition that, or with your basics being very strong, that if you short it, output voltage should be 0, but that's not being captured here. Where are we missing? Are we missing something? Then this is correct, right? It's a function of load. Output voltage is a function of load, input and duty cycle. But this equation does not tell. Right? The reason is, when you derive something, you should also know its limits. You should also know when was that equation derived. This equation was derived assuming everything is very nice. You're not in dynamics. You're in steady state. So this is going to tell you only steady state. What it says is, look, if you have a converter, and then you change this load, not too much, you change it 20%, 30%, your output voltage, the steady state output voltage will remain the same. That is called as continuous conduction mode. In all the continuous conduction modes and any power converters that you look at, your output voltage, when you look at a derivation, is independent of the load, which says variation in load is not to be too much worried if it is in continuous conduction. Is that clear? But there are dynamics associated. What it says is, look, if you vary the load by some value, not too much, no drastic conditions like you open circuit it or short circuit it, but under some conditions, you will see dynamics, but then naturally this goes and settles down to its steady state. You don't have to do anything. Why? Because it is not so much dependent on the load. That is what this equation is going to tell you. But doesn't mean you short the load or you open circuit it, you will still have the output. You have very drastic conditions if you open circuit. In case if you look at a boost converter and then you open the load for some time, your capacitor just blasts in 2 or 3 switching cycles, which is in kilohertz or in milliseconds. So within a certain range of variations in the load, your output voltage will still remain constant. Is that clear? But what are we talking about is dynamics. In dynamics, this matters to me. Though it goes to steady state, what happens matters to me. That's the reason I've still accounted for the load. So we have variations in input, we could be variations in load, there could be variations in the duty cycle. All of this would contribute to my output voltage. So whenever you design a power converters, you should always ask your customer 3 important things. What is my variation in input? He should give you this constraint. He should tell you, look, the nominal voltage is 230 volts, but then it varies by 20%. And he should also tell you what is the load change. What is the percentage change in the load. He cannot say, I'm going to short the load, give me 13 volts. It's not according to the law of Ohm's law, right? It's not according to Ohm's law. You have R equal to 0, want to maintain the voltage. V equal to I into R, there is no equality. He cannot say that. Then based on this, it's a duty cycle. He should also tell you what is the minimum and maximum duty cycle that you should be working with. That's called this Dmin and Dman. Dmin and Dmax. So all the 3 will contribute to the control system designs. Is that clear? So this slide is so much. Is that clear? Okay. one very good example is, see, I don't mind whether today we successfully design the entire controller, but what I want is you understand the basis with which you design. Nobody wants you to design controller in the first go. They want you to understand the problems that are associated with the controllers. Of course, the idea is to design the entire controller, but more than the controller design, I want you to understand this. Now, the same controller, we know this is the most notorious thing we will concentrate on. Let's consider a case study where this VG varies. Okay? So, the application that I have considered is this. This is very relevant to today's topic because it also falls, it's a very important converter in your electric vehicles. It's called as a rectifier fed converter, also called the PFC converter, power factor correction converter. You're all from power systems, so I don't have to tell you what power factor is. You will yourself can train me more on power factors. I can ask you doubts if I have. So you know so much of power factor because you always want the power factor to be good, right? Okay. So one question is, why should we want the power factor to be high? Why is that we don't want power factor to be 0.2 or 0.1? Why you want 0.8, 0.91? How do you define efficiency? Can you just tell me efficiency? How do you relate efficiency and power factor?
We have good power factor will be having less current and hence less losses.
Okay, that's correct.
Efficiency is equal to output by input.
So you have better efficiency. That's good. So in other ways, for a given active power that your load demands, you don't have to provide too much of kVA, right? The best thing if you have a very good power factor of 1 is your kVA equals or your VA rating equals your load demand, active power demand. Okay, so you know that definition. That definition is very, very, very important for all of us. So there is an entirely, I'll tell you about my company. Let's say we have 100 employees working in electric vehicles. 60 to 70 people are working only on correcting the power factor. This guy who is just, phase difference between voltage and current is so notorious that I fall under the last 40 people who don't work on this, because anybody who works on power factor is considered to be someone who's an expert, because this is not that easy to deal with. And this definition is there right from your 12th or from your first year you study power factor. But to correct this power factor is not at all easy. I'll tell you why. And this is the motivation for us to design controller for today. At the end, we should be able to approach this problem, right? And that should be able to read. I mean, whenever you read electric vehicles, you come across power factor because that's the front guy. So whenever you enter a code, right, you will have to first bear the security, right? So this guy is that. EV starts with power factor correction. The first converter that you look at any papers in EV starts with power factor correction, right? So without power factor correction, you cannot sell your EVs. I'll show you how bad is this power factor. Okay, so let's take up this example of power factor correction and show you how notorious this VG is and what impact it has on the output. So let's come to this point as to why we need, why is this converter like this? Yeah, why is this converter like this? That's not a problem. Don't bother about it. But you look at it, this is a boost converter, right? Inductor, switch, and diode. If you look from the other side, it's a buck converter. It's basically the same. So important thing is you have the AC voltage. This is the AC, which is your outlet or socket, and then you have a diode rectifier, right? Now the diode rectifier output is going to be something like this, correct? It's a pulsating output. Then you have some mysterious converter, a power factor converter. Then you have some DC-DC converter, and this is given to a load. Now what is of interest is this, right? This point. So let's say I don't have any idea of power factor correction, power factor converter, because I don't know why this converter is required. Right? We are in that mode now. So we have an AC source, we have a diode rectifier. We'll only consider this. Okay. Now why do we need this? This is going to be the front end because I'm talking about DC-DC converter, right? I'm talking about DC-DC converter. So DC-DC converter needs DC input. What I have is AC. How do you convert AC to DC? Rectifier. The simplest, no, the most taken for granted converter, right? So let's look at only this. Okay? Yeah. Now this, wherever you want DC output, wherever you want DC input, right? That DC what I'm talking about, this DC. Wherever I want DC input that I've put on the board, the first guy that you will encounter is this. You will need him. You will need this person, right? Voltage source and a diode rectifier. Now, whatever application that I have considered could be an EV charger, or could be a laptop chargers, or your mobile phone chargers. Okay? Right from anywhere from mobile chargers till wherever, you will see this. So what you have on the front is that a diode rectifier, but okay, what you see is a diode rectifier here. That is your socket. That plug connection that you see, all of these connections that you see here, they are that input to your diode rectifiers. Okay? And then you have the diode rectifier in your charger. Okay? What I have considered is 65 watts charger applicable to anything. Now, if you just connect your diode rectifier without this capacitor, if you connect it here, okay, you have a diode rectifier connected here. What do you see? What will happen to this point? How will the output voltage look like? Pulsating. But do you want a pulsating input to your buck converter? No, you don't want. So what will you do? Add a capacitor, right? You want a capacitor, so you add this capacitor. It's called smoothing capacitor. So you can see that the pulsating output has now become a very smooth output. Ideally, infinite capacitance will give you flat DC. Okay? Are we happy? Are we happy if we designed the input to your DC-DC converter? Is it good? We have a let's say we have put infinite capacitance and then we have got a smooth DC. Can I connect it to my buck converter? Just what do you feel? Can I do it? Yes, it's pretty possible. Well, don't think too much. Sometimes you think too much is too bad. Just connect it happily. Let's see what happens later. You can connect it. There is no problem at all. See, I have happily connected to the load, right? This load is a buck converter. Now, power electronic people are very happy because they have designed a wonderful power supply. Don't have to worry about diode rectifier because diode rectifier knows when to turn on and when to turn off, right? They know when to go to sleep mode and to wake up mode. You don't have to control. Power electronics are very happy because you've got a very beautiful waveform. But power system people, they have a concern. They say, no, you can't do this. Can you tell me why? Power system people will probably raise a strike. They tell we are not allowing you to do this.